so they can do self-play in reality. So we're actually pulling that out. So we're going to have at least 10,000 Optimus robots, maybe 20 or 30,000 that can do that are doing self-play and testing different tasks.
Tesla Optimus Gen 3 robot is set to debut this July with at least 5 major upgrades. More importantly, it's expected to be the final production-ready version, capable of handling up to 100 expanded tasks every day, thanks to its ability to learn on its own and share knowledge with other Optimus robots. Elon Musk has confirmed that Tesla is building what's called the Optimus Academy, a dedicated training system for the robot. According to Musk, Optimus could eventually cook your daily meals or even make you breakfast like a real household assistant. With just a single voice command, it could also clean your entire home. But that's only the beginning. Musk has repeatedly emphasized that Optimus Gen 3 is designed to achieve human-level precision in a wide range of tasks. So what makes this version so exciting, and how quickly will it be able to complete everyday jobs? Here's everything you need to know. Right now, the Optimus robots Tesla has been demonstrating are still version 2.5. Musk recently clarified this on X, saying, "We haven't shown Optimus 5.3 yet. It is sublime. The second 2 images are V2 and V2.5.
Yeah, but I think Optimus 3 is the right version of the robot to produce maybe something on the order of like 1 million units a year.
A lot of people are still confused about the different Optimus versions. In reality, Optimus version 2.5 already introduced several noticeable improvements over its predecessor. Its exterior has been redesigned with smoother lines, cleaner joint covers, and far fewer exposed cables. The overall design has shifted away from a boxy, industrial look towards softer, more rounded shapes, making the robot appear friendlier and much closer to a finished consumer product than an engineering prototype. Beyond the visual upgrades, Optimus 2.5 is now integrated with xAI's Grok voice assistant. It can answer spoken questions.
Hey Optimus, do you know where I can get a Coke?
Sorry, I don't have real-time info, but I can take you to the kitchen if you want to check for a Coke there.
Although its responses still aren't particularly fast, and there's a noticeable delay. The conversations can sound a little hesitant and awkward at times, but it's still a significant leap forward compared to previous versions. Now, when it comes to Optimus 3, Elon Musk has hinted that this generation will feature an extraordinary design optimized for mass production. It will reportedly walk more naturally, be powered by Tesla's AI-5 computer, feature even more human-like hands, and look much less like an early prototype. But if you read between the lines of what Musk has been saying, the most impressive part isn't that Optimus can walk, and it isn't that it can talk. It's that Optimus is getting very close to the point where it can actually work like a human. So how will Optimus 3 be able to cook meals, clean an entire house, and handle tasks that are far more complex than anything previous versions could do? If you look at many of the humanoid robots coming out of China, you'll notice something interesting. They can run incredibly fast, perform amazing backflips, box, dance, and pull off all kinds of athletic stunts. Sure, those videos are impressive, but once the excitement wears off, one practical question still remains. Can they actually do anything useful in everyday life? Just because a robot can dance doesn't mean it knows how to wash a single plate. A robot that can sprint across a room may still crush an egg the moment it tries to pick one up. And a robot that can do backflips might still have no idea how to open a refrigerator, grab the right ingredients, turn on the stove, place a pan on the burner, control the cooking temperature, and wipe down the counter when it's finished. And that's exactly where Tesla is aiming. Elon Musk has repeatedly said that Optimus 3 wasn't built to put on a show. It was built to do the jobs people don't want to do, don't have time to do, or simply shouldn't have to do. Boring, repetitive, physically demanding, or dangerous work. But to make that vision a reality, Tesla has to solve one of the hardest problems in robotics, teaching a robot to operate in a world that was designed entirely for humans. Optimus has to understand its surroundings. It needs to know where the refrigerator is, where the handle is located, how an egg is different from a tomato, which part of the frying pan to grab, how much force to apply, how much cooking oil to pour, how hot the stove is, and exactly when the food is done. For us, those actions feel almost effortless. We don't consciously think about them. But for a robot, every one of those steps is a complex chain of decisions. Grip an egg too tightly, and it cracks. Hold it too loosely, and it slips out of your hand. Rotate the wrist at the wrong angle, and dinner ends up on the floor. React just half a second too late when someone walks into the kitchen, and the robot could become a safety hazard. That's why cooking isn't just another cool demo. It's proof that a robot is beginning to understand and interact with the physical world the way humans do. And that's exactly why the next-gen hands-on Optimus Gen 3 matter so much. With Optimus 2.5, Tesla has already increased the robot's walking speed to around 2.6 miles per hour, while significantly upgrading its leg actuators and battery pack. But Optimus Gen 3 is expected to raise the bar even further, although it hasn't been officially unveiled yet. Elon Musk has already hinted at what could be one of the robot's biggest breakthroughs, a next-generation pair of hands that Tesla believes will set a new standard in humanoid robotics. After all, a robot that can walk but can't manipulate objects with precision is still little more than an expensive demonstration. That's where many humanoid robots, especially those focused on flashy athletic performances, still fall short. They've invested heavily in mobility. But the real challenge has always been the hands, because in the end, it's the hands that determine whether a humanoid robot is actually useful. Everyday tasks like wiping a table, folding laundry, picking up a glass of water, unscrewing a bottle cap, collecting children's toys, loading dishes, or cooking, all depend on one thing: hands that are strong enough to handle weight, sensitive enough to feel what they're touching, precise enough to perform delicate movements, and durable enough to operate reliably in all kinds of real-world environments. Tesla is reportedly pushing Optimus Gen 3 toward a next-generation hand with 22 degrees of freedom. That number matters because it allows the robot's hands to move with far greater dexterity than traditional industrial grippers. But degrees of freedom are only part of the equation. The real challenge lies in the actuators, the mechanical muscles that power every joint and every finger movement. Elon Musk has said that building a truly dexterous robotic hand is already incredibly difficult. But manufacturing hundreds of thousands or even millions of those hands at a consistent level of quality is exponentially harder. That's the difference between a prototype and a real product. Building a robotic hand that works in a laboratory is one thing. Building a million identical hands that are affordable, durable, and precise enough for mass market production is an entirely different engineering challenge. Instead of assembling Optimus from off-the-shelf components, Tesla is developing custom actuators for different parts of the robot's body. The hips, shoulders, wrists, and fingers all have very different jobs, so they shouldn't be powered by the same type of actuator. The hips need massive torque to support the robot's weight and maintain balance. The shoulders have to deliver smooth, natural motion. The wrists require flexibility and a wide range of movement, and the fingers demand extreme precision for delicate manipulation. If every joint used the same actuator, the robot would likely end up heavier, slower, more expensive, and far less efficient. But by optimizing each actuator for its specific role, Tesla has a chance to build a humanoid that's dramatically more capable in the real world. Of course, even the most advanced hands aren't enough on their own. Optimus Gen 3 also needs a brain that's fast enough to understand and respond to the world in real time. And that's exactly why the move to Tesla's new AI-5 computer could completely change the game. AI-5 could end up being the single most important upgrade for Optimus Gen 3, not because it sounds impressive, but because a robot can't rely entirely on the cloud. If Optimus is carrying a tray of food, it can't wait for a Wi-Fi response to decide whether to stop when a child suddenly runs in front of it. If it's holding a glass, it can't upload data to a server and wait for an answer about how much force to apply. Those decisions have to happen instantly, inside the robot itself. Self-driving cars are already incredibly difficult because they have to perceive the road, recognize other vehicles, pedestrians, traffic lights, and signs, then react in real time. But humanoid robots add an entirely new layer of complexity. They don't just observe the world, they physically interact with it. They have to handle real objects with real weight, real friction, and real people in environments that are never perfectly predictable. Put simply, a self-driving car needs visual intelligence. Optimus needs both visual intelligence and motor intelligence. And when those two systems have to run simultaneously, the computational challenge becomes exponentially greater. That's why Tesla is prioritizing AI-5 for Optimus. If the chip can truly process massive amounts of data locally while maintaining low power consumption, it will make Optimus faster, safer, and far more autonomous. This isn't just another hardware upgrade. It's the key to taking Optimus beyond carefully staged demo videos and into real-world work environments. So how will Optimus Gen 3 learn 100 tasks per day? Yeah, that's exactly the problem Optimus Academy is designed to solve. The reality is that Tesla isn't trying to manually program every possible situation a robot might encounter. Instead, they're building a data flywheel. The idea is simple. Optimus goes to work, makes mistakes, and learns from them. Tesla collects data from those mistakes, improves the software, and pushes updates back to the fleet. Every update makes the robots a little better. The real advantage is that when one robot learns a new skill, that knowledge doesn't stay with just that robot. It can be shared across the entire fleet. For example, one Optimus might learn how to transport parts inside a factory. Another could learn how to serve food at Tesla Diner. A third might spend its day vacuuming someone's house. Every one of those experiences is fed into a centralized learning system. That's essentially how Optimus Academy works. If Optimus were just a standalone robot, learning would be painfully slow. Even after spending $30,000 on one, you'd still have to train it yourself. But if Tesla deploys thousands of robots across factories, restaurants, warehouses, and charging stations, the system will generate an enormous amount of real-world data about physical labor every single day. And the more robots are working, the faster the entire fleet learns. But to realistically assess the Optimus Gen 3, we can't just look at Tesla's promises. The current humanoid robot race has very specific competitors with very specific specifications. Boston Dynamics has Atlas, an industrial robot about 6.2 feet tall, weighing about 198 pounds, with 56 degrees of freedom, a reach of about 7.5 feet, and a battery life of about 4 hours. In China, Unitree takes a completely different approach. The Unitree G1 is only about 4.3 feet tall, weighs 77 pounds, has 23 to 43 degrees of freedom depending on the version, a battery life of about 2 hours, and a starting price of around $13,500. The Unitree R1 is even more shocking, starting at $4,900. These numbers make the race much clearer. Atlas is not just a beautiful robot for show. As a heavy-duty industrial robot with 56 degrees of freedom, flexible maneuverability, a large payload capacity, and an IP67 rating, Atlas is built for use in factory, warehouse, and production line environments, making it a formidable choice. However, these specifications also suggest that Atlas is targeting a different market than Optimus. A robot like Atlas would be very powerful in a factory, but not necessarily suitable for the kitchen of an average family. Unitree, on the other hand, puts pressure on Tesla in the opposite direction, a price pressure even Elon Musk has acknowledged. To be honest, a humanoid robot priced under $5,000 like the R1 immediately changed how the market viewed robot costs. While the R1 cannot yet be considered a complete service robot, it demonstrates that humanoid form, basic movement, cameras, microphones, speakers, processors, and joints can be packaged at a much lower price than previously imagined. This forces Tesla to be cautious. If the Optimus Gen 3 launches at an excessively high price, viewers will no longer be easily convinced by the promise that someday the price will drop to $20,000 to $30,000. Tesla has a very clear path to commercialization. Optimus doesn't need to do everything from day one. It just needs to perform a handful of repetitive, economically valuable tasks really well. Every time a robot successfully completes a task, the data feeds back into the system. As the system improves, those new skills can be deployed across the entire fleet. That's the advantage Tesla is trying to build, not just selling individual robots, but creating a continuously learning robotic network where every robot benefits from the experience of the others. More than 150 Cybercabs are now driving throughout Gigafactory, Texas, with each vehicle autonomously traveling about 1.5 miles from the production line to the end-of-line fast charging stations before final delivery. At the same time, Cybercabs have been spotted on the streets of San Francisco and Las Vegas, while Elon Musk recently shared a video of a Cybercab with no steering wheel or pedals driving on public roads in Austin. All of this shows that Tesla is rapidly moving closer to large-scale robo-taxi deployment. But amid these milestones, there's something even more important that few people have noticed. Have you spotted the Cybercab's latest upgrades and why they could give Tesla an edge that rivals will struggle to match? Battery configuration. The most important upgrade is actually one that passengers will never see. Tesla has completely replaced the traditional 12 to 16 volt low-voltage electrical architecture with a 48-volt lithium-ion system that powers the Cybercab's computers, sensors, and electronic components. This is far more than a technical improvement. It is the electrical foundation that could enable Tesla to scale its robotaxi fleet to millions of vehicles while lowering manufacturing costs, improving efficiency, and increasing long-term reliability. A single Cybercab must continuously power dozens of high-resolution cameras, the FSD AI computer, electronic control units, the climate control system, a 5G modem, safety sensors, door locks, lighting, and hundreds of other electronic modules for nearly 24 hours a day. If it continued using a 12-volt system, the electrical current flowing through the wiring would be much higher, generating more heat, wasting more energy, and requiring significantly thicker copper cables. By increasing the voltage to 48 volts, Tesla reduces the current by approximately 75% while delivering the same amount of power. According to Joule's law, electrical losses increase with the square of the current, so this change dramatically reduces heat generation and significantly improves overall efficiency. The benefits extend well beyond efficiency. Tesla can also reduce the vehicle's wiring weight by roughly 30% to 50%. A modern vehicle typically contains between 1.5 and more than 2 kilometers of wiring, weighing several dozen kilograms. If each Cybercab saves around 15 to 20 kilograms of wiring, and Tesla eventually reaches Elon Musk's goal of producing 1 million robotaxis per year, the company could save tens of thousands of tons of copper. With industrial copper prices remaining high, this single engineering decision could save Tesla billions of dollars in raw material costs over time, while simultaneously reducing vehicle weight, improving efficiency, and extending driving range. Even more importantly, the 48-volt architecture provides a far more stable power supply for Tesla's FSD computer. A driverless robotaxi must process billions of calculations every second to identify pedestrians, cyclists, traffic lights, and thousands of other objects in real time. Any voltage drop could reduce the AI system's processing performance. Thanks to the higher operating voltage, Cybercab can maintain a stable power supply even while accelerating, braking hard, running the climate control system, and handling highly complex driving situations simultaneously. It is no coincidence that premium automakers such as Mercedes-Benz, Porsche, and Rivian are also transitioning toward 48-volt electrical architectures. However, Tesla may become the first company to deploy this technology across a robotaxi fleet capable of operating nearly 20 hours a day. It may be one of the least visible upgrades, but it could also become one of the biggest reasons why Cybercab achieves lower operating costs than nearly every competing robotaxi. If Cybertruck already uses an 800-volt system, why did Cybercab stay with a 400-volt architecture? At first glance, keeping a 400-volt high-voltage system instead of upgrading to 800 volts may appear to be a technological step backward. In reality, it represents the exact opposite. It reflects Elon Musk's long-standing engineering philosophy. Never choose the most expensive technology. Choose the technology that delivers the greatest economic value. A robotaxi operates very differently from a privately owned vehicle. While EV owners value ultra-fast charging during long-distance travel, Cybercab is designed to operate as part of a centrally managed fleet. It can automatically return to a depot during off-peak hours for charging and may eventually support autonomous wireless charging. As a result, the faster charging capability of an 800-volt architecture becomes far less important than it is for consumer vehicles. Meanwhile, Tesla's 400-volt platform has already been validated through millions of Model 3 and Model Y vehicles that have accumulated tens of billions of real-world driving miles. Its silicon carbide inverters, power electronics, and entire supply chain have been optimized through years of high-volume production. By continuing to use this mature platform, Tesla avoids rebuilding its manufacturing infrastructure, significantly reduces component costs, and accelerates production scaling. This is also an advantage that many competitors will struggle to replicate. Most robotaxi developers must build entirely new vehicle platforms while producing only hundreds or thousands of units each year, resulting in much higher costs. Tesla, by contrast, leverages nearly the entire component ecosystem already supporting the world's best-selling electric vehicles. As production volume increases, the cost of each Cybercab continues to fall through economies of scale. Tesla has also eliminated wireless phone charging in favor of high-power USB-C ports. Although this appears to be a small change, it reflects Tesla's obsession with optimization. Wireless chargers consume standby power, generate unnecessary heat, and often fail when a phone's not perfectly aligned. USB-C charging is faster, more reliable, and less prone to failure in a robotaxi that may serve dozens of passengers every day. If a fleet of 1 million Cybercabs eliminates just a few tens of dollars in components per vehicle, Tesla could save tens of millions of dollars in manufacturing costs alone, not including years of reduced maintenance expenses. Camera cleaning system. For a human driver, a small smudge on the windshield may be nothing more than a minor annoyance. But for a driverless robotaxi, even a single obstructed camera can significantly reduce its ability to perceive the surrounding environment. That is why Tesla treats its camera cleaning system not as an optional convenience, but as a core technology that directly determines the vehicle's ability to operate at SAE Level 4 autonomy. According to Tesla's technical documentation, every exterior camera on the Cybercab is equipped with its own dedicated cleaning system, featuring both a washer nozzle and a high-pressure compressed air jet. Instead of simply rinsing the lens like many conventional automotive camera systems, Tesla uses compressed air to instantly blow away rainwater, fine dust, mud, and other debris from the camera lens. This allows the cameras to quickly regain a clear field of view without any human intervention. This is an extremely important advantage because Cybercab relies entirely on computer vision. Tesla has repeatedly emphasized its vision-only philosophy, meaning the AI primarily uses camera data to understand the surrounding environment rather than depending on expensive LiDAR sensors, like many competing autonomous driving systems. As a result, image quality must remain consistently high. Even a thin layer of ice, a splash of mud, or bird droppings on a single camera lens could reduce the accuracy of the vehicle's object recognition algorithms. Tesla addresses this challenge through a fully automated cleaning network. Whenever the system detects degraded image quality or recognizes that a camera lens has become obstructed, the affected camera is cleaned immediately without requiring the vehicle to stop. This capability is especially critical for a robotaxi that may operate for nearly 20 hours a day, because every minute spent pulling over for manual sensor cleaning represents lost revenue. Thanks to this system, Tesla says Cybercab can operate both day and night in light to moderate rain, fog, and snowy conditions. It is also designed to drive autonomously on highways, city streets, rural roads, multi-level parking garages, airport pickup zones, and even through automated car washes. While many existing robotaxi programs still restrict their operating areas or significantly reduce speed during poor weather, Tesla is working to expand its operational design domain, the range of environments in which the vehicle can safely operate autonomously to maximize vehicle utilization. For a transportation business, increasing operating time by just a few percentage points each day can translate into a substantial increase in revenue when multiplied across tens of thousands of vehicles. Fleet maintenance features. Tesla's engineering focus extends far beyond software and artificial intelligence. The company has also redesigned numerous mechanical details specifically to simplify maintenance and support fleet operations on an unprecedented scale. These upgrades may receive little public attention, but they could significantly reduce vehicle downtime, one of the most important factors affecting robotaxi profitability. Tesla uses bright orange battery coolant, allowing technicians to identify leaks within seconds instead of manually inspecting every cooling line. If the charging connector malfunctions during charging, Cybercab includes a manual emergency charging cable release located behind the rear wheel well liner, enabling technicians to disconnect the charging cable quickly without disassembling major body components. Although these improvements appear minor individually, they can substantially shorten repair times, especially when Tesla is managing tens of thousands of continuously operating vehicles. Cybercab also differs significantly from Tesla's existing consumer vehicles when it comes to towing procedures. The vehicle must be transported with all four wheels off the ground to protect its electric drive system and motors. To simplify roadside recovery, Tesla has integrated a dedicated tow strap and a carabiner attachment point behind the front license plate. With only a few simple steps, recovery crews can access the towing point without removing the front bumper or other complex body panels. Another notable upgrade is the distinctive yellow wheel covers. Beyond serving as a recognizable design element, they extend outward to protect the tire sidewalls from curb damage, a common issue for urban taxi fleets. When technicians need access to the wheel nuts or tire valve, they simply pull on the flexible outer ring to remove the entire cover within seconds. Across millions of maintenance operations over the lifetime of a large robotaxi fleet, saving just 1 or 2 minutes per service procedure could eliminate hundreds of thousands of labor hours every year. Perhaps the most significant upgrade, however, is Cybercab's ability to manage unexpected failures autonomously. When no passengers are on board, the vehicle can drive itself to a parking area, charging station, or service center without human assistance. If it detects a hardware malfunction or loses connectivity, the system immediately activates its hazard lights, evaluates the surrounding traffic environment, safely pulls over to the roadside, and then contacts Tesla's remote operations center. This represents a major leap beyond today's advanced driver assistance systems, which still require a human driver to take control whenever a critical fault occurs. Ultimately, this ability to continuously monitor itself, protect its occupants, and make intelligent decisions during unexpected situations may become the defining factor that allows a robotaxi to operate for dozens of hours each day without a human driver behind the wheel.